Imagine a planet so reflective it acts like a cosmic mirror, a world where metallic clouds shimmer across the sky, bouncing back nearly every photon of light that touches them. A place so bright that if you could somehow survive on its surface, you'd be blinded by the glare of your own star reflected back at you 1,000 times over. This isn't science fiction. This planet exists, and it's one of the strangest objects astronomers have ever discovered. In 2020, scientists announced the detection of LTT 9779b, an exoplanet orbiting a star about 260 light-years from Earth. At first glance, it seemed like just another hot Neptune, a gas giant slightly smaller than Neptune, scorched by proximity to its star. But when researchers measured how much light it reflected, they found something that shouldn't be possible. This planet reflects about 80% of the light that hits it. That's more reflective than Venus, the brightest planet in our solar system. More reflective than fresh snow. More reflective than polished silver. In fact, LTT 9779b is the most reflective exoplanet ever discovered, and possibly the most reflective large object in the entire universe. You're looking at a world that defies our understanding of how planets should behave. It's too hot to have clouds, too close to its star to maintain an atmosphere, too massive to exist in the orbital zone where we find it. And yet, there it is, a gleaming jewel in the cosmic darkness, reflecting the light of its star like a mirror floating in space. This is the story of how we found it, why it exists, and what it reveals about the infinite variety of worlds scattered across the universe. The story begins with a space telescope that most people have never heard of. Cheops, the characterizing exoplanet, satellite launched by the European Space Agency in 2019. Its mission is specialized to study planets that have already been discovered, measuring their sizes, densities, and other properties with extreme precision. LTT 9779b had been detected before Cheops arrived. Ground-based telescopes had spotted the slight wobble in its star's motion caused by the planet's gravity, and the tiny dip in starlight when the planet passed in front of its star. We knew it was there. We knew roughly how big it was and how close it orbited. But we didn't know it was a mirror. When Cheops turned its instruments toward LTT 9779b, it wasn't just measuring the dip in starlight as the planet transited its star. It was also watching for something more subtle, the secondary eclipse. This is the moment when the planet passes behind the star from our perspective. If the planet is reflecting significant amounts of light, you'll see a tiny additional dip in the total light from the system when the planet disappears behind the star, because you've lost not just the star's light, but also the light the planet was reflecting. The data came back, and astronomers had to double-check their calculations. The secondary eclipse was huge, far larger than anyone expected. This planet wasn't just reflecting some light, it was reflecting almost all of it. Follow-up observations confirmed it. LTT 9779b has an albedo, a measure of reflectivity, of about 0.8. That means it reflects 80% of the light that strikes it. For comparison, Earth reflects about 30% of sunlight. Venus, our solar system's most reflective planet due to its thick sulfuric acid clouds, reflects about 75%. This exoplanet is even brighter. You're witnessing a world that shouldn't exist according to our models of planetary atmospheres. And the more scientists studied it, the stranger it became. So what makes LTT 9779b shine like a cosmic mirror? The answer lies in its clouds, but not the kind of clouds you're familiar with. On Earth, clouds are made of water droplets or ice crystals. On Venus, they're sulfuric acid. On Jupiter and Saturn, they're ammonia and methane. These are all substances that condense at relatively cool temperatures. But LTT 9779b is anything but cool. This planet orbits its star once every 19 hours. That's not a typo 19 hours for a complete year. It's so close to its star that the side facing the star reaches temperatures around 1,700 degrees Celsius, hot enough to melt aluminum, hot enough to vaporize most materials we think of as solid. At these temperatures, water clouds can't exist. They would instantly evaporate. Even the exotic clouds of hot Jupiter's gas giants that orbit close to their stars typically can't form in this heat. Scientists call this the hot Neptune desert, a region close to stars where Neptune-sized planets are extremely rare, probably because the intense radiation strips away their atmospheres over time. But LTT 9779b has found a way to survive, and it's done so by creating clouds made of materials that remain solid or liquid at extreme temperatures. The leading theory is that the clouds are composed of tiny droplets or crystals of silicates, essentially molten glass, mixed with metallic compounds like titanium. These materials have extremely high melting points and can survive in the inferno of the planet's upper atmosphere. When they condense into clouds, they create a reflective layer that acts like a mirror, bouncing starlight back into space before it can heat the deeper atmosphere. It's a feedback loop of survival. The reflective clouds prevent even more heat from penetrating, which allows the clouds to persist, which keeps the planet reflective. Remove those clouds, and the planet would absorb more energy, heat up further, and likely lose its atmosphere entirely to the stellar wind joining the graveyard of stripped planets in the hot Neptune desert. You're looking at a planet that has engineered its own survival through the physics of reflection. Its brightness isn't just a curiosity, it's a defense mechanism against obliteration. Here's the problem that keeps planetary scientists awake at night. LTT 9779b shouldn't be there. The hot Neptune desert is called a desert for a reason. When astronomers survey thousands of exoplanets, they find a conspicuous gap. Close to stars, you find small rocky planets like super-Earths. You also find hot Jupiters, massive gas giants that somehow migrated inward from where they formed. But Neptune-sized planets in tight orbits, they're vanishingly rare. The physics makes sense. A planet like LTT 9779b is massive enough to have held onto a thick atmosphere when it formed, but not massive enough to gravitationally anchor that atmosphere against the onslaught of stellar radiation. Over millions of years, the star's ultraviolet light and charged particle wind should strip away the atmosphere layer by layer, eventually leaving behind a bare, rocky core. This process, called photoevaporation, is extremely efficient at these orbital distances. Models predict that Neptune-sized planets this close to their stars should lose their atmospheres within a few 100 million years at most. LTT 9779 star is about 2 billion years old, meaning this planet has been enduring this bombardment for far longer than it should be able to survive. And yet it's still here, still massive, still wrapped in a thick atmosphere of metallic clouds. How? The reflective clouds are part of the answer. By bouncing back 80% of the incoming light, the planet reduces the amount of energy absorbed by the atmosphere. Less energy means less heating, which means slower atmospheric escape. The planet is literally shielding itself with a mirror. But there's likely more to the story. Some scientists suspect the planet might be unusually massive for its size, packed with a dense core that provides extra gravitational pull to hold the atmosphere in place. Others think the star itself might be less active than typical stars of its type, producing fewer of the high-energy particles that drive atmospheric loss. Or perhaps LTT 9779b formed differently than other planets. Maybe it migrated inward more recently, and we're seeing it during a temporary phase before it too succumbs to the desert. Or maybe it's replenishing its atmosphere somehow, volcanically outgassing materials from its interior to replace what's being lost. We don't have all the answers yet. What we do know is that this planet is an outlier, an exception to rules we thought were ironclad. And exceptions are where science gets interesting, because they force us to rewrite the rules. Finding a planet 260 light-years away is one challenge. Determining that it's covered in metallic mirror clouds is another entirely. You can't see exoplanets directly in most cases. They're too small and too dim compared to their stars. It's like trying to spot a firefly next to a searchlight from across a city. Instead, astronomers use indirect methods, looking for the subtle effects planets have on their stars. The transit method, watching for the dip in a star's brightness as a planet passes in front, tells you a planet exists and gives you its size. If you observe many transits, you can even detect the presence of an atmosphere by analyzing how the star's light filters through the planet's atmosphere, leaving chemical fingerprints in the spectrum. But measuring reflectivity requires something more sophisticated. Detecting the secondary eclipse. When the planet goes behind the star, you lose a tiny fraction of light. Not just the starlight the planet was blocking, but also the starlight it was reflecting back toward you. That difference, measured with extreme precision, reveals how reflective the planet is. Cheops was built for exactly this kind of measurement. Its detectors are sensitive enough to measure changes in brightness of just a few parts per million. It can stare at a single star for hours or days, building up the data needed to detect these subtle signals. For LTT 9779b, the signal was anything but subtle once the data was analyzed. The secondary eclipse showed a clear, measurable dip, the signature of a highly reflective world. Further observations using ground-based telescopes and spectroscopy confirmed the presence of the metallic clouds, identifying the chemical signatures of titanium and silicates in the planet's atmosphere. This is modern astronomy at its finest. You're not looking through a telescope and seeing planets with your eyes. You're analyzing rivers of data, measuring light curves, hunting for patterns in noise. The universe reveals its secrets not through direct observation, but through inference, calculation, and the patient accumulation of evidence. And sometimes when you gather enough evidence, you discover that reality is stranger and more beautiful than you imagined. A planet made of mirrors. A world that gleams. Every exoplanet we discover teaches us something about the diversity of worlds in the universe. LTT 9779b is no exception, but its lessons are particularly profound. First, it reminds us that planetary systems are far more varied than we once imagined. Before the 1990s, the only planetary system we knew was our own. Small rocky planets close to the sun, gas giants farther out, everything on roughly circular orbits. It seemed orderly, logical, perhaps even typical. Then we started finding exoplanets, and that illusion shattered. Hot Jupiters in 3-day orbits. Super-Earths larger than Earth, but smaller than Neptune, a type of planet that doesn't exist in our solar system. Worlds orbiting binary stars, planets with orbits tilted perpendicular to their star's equator, systems with planets packed so tightly they'd fit inside Mercury's orbit. And now, a Neptune-sized planet in a hot desert, surviving through reflective armor. Each new discovery expands the parameter space of what's possible, revealing that the universe's creativity far exceeds our theoretical imagination. Second, LTT 9779b challenges our models of atmospheric evolution. If a planet can maintain a thick atmosphere this close to its star by being reflective enough, that opens new possibilities for where we might find habitable worlds. Perhaps some rocky planets in the habitable zones of other stars use similar mechanisms, highly reflective cloud layers to regulate their temperatures and maintain stable climates suitable for life. Understanding the physics of LTT 9779b's survival might help us identify other planets that have beaten the odds, worlds we'd otherwise dismiss as too hostile or unstable. Third, it highlights the importance of albedo in planetary science. Reflectivity isn't just an aesthetic property, it's a fundamental factor in a planet's energy budget. How much light a world reflects versus absorbs determines its temperature, atmospheric dynamics, climate patterns, and ultimately its habitability. Earth's ice ages and warm periods are partially driven by changes in albedo as ice sheets advance and retreat. Venus's greenhouse effect is amplified by its bright clouds, which trap heat below while reflecting light above. LTT 9779b is an extreme case study in how albedo can mean the difference between survival and obliteration. Finally, this planet reminds us that we're still in the early days of exoplanet science. We've discovered over 5,000 exoplanets, but there are billions in our galaxy alone. Each one is unique, a world with its own history, its own physics, its own story. Some will resemble Earth, many will be utterly alien, and a few, like LTT 9779b, will be so strange they force us to rewrite our textbooks. You're living in the era when humanity first learned it's not alone in having planets. And we're discovering that the cosmic neighborhood is far weirder and more wonderful than anyone predicted. 260 light-years from Earth, a planet shines. It's not shining with its own light. Planets don't produce light, only reflect it. But LTT 9779b reflects light with such intensity, such perfection, that it might as well be a star in its own right. If you could somehow travel there and approach it, you'd see your own ship reflected in the planet's metallic clouds, distorted and multiplied by the swirling patterns of exotic weather systems, unlike anything in our solar system. You'd see a world that defies easy categorization. Not quite a gas giant, not quite an ice giant, not where it should be, not configured the way models predict. Just existing, surviving, gleaming a testament to the universe's capacity to find solutions to problems we haven't even fully understood yet. This planet is a mirror in more ways than one. It reflects light, yes, but it also reflects back to us our incomplete understanding, our hubris in thinking we've figured out how planets work. It shows us that nature is more inventive than our theories, that the universe contains multitudes of worlds we haven't imagined yet, and it reminds us why we explore, not just to catalog objects in space, but to encounter the alien, the unexpected, the sublime, to find worlds so strange they expand what we think is possible. LTT 9779b is one planet around one star in a galaxy of hundreds of billions of stars. There are countless other worlds out there, each with its own peculiarities, its own defiances of expectations. Some might be even more reflective, though it's hard to imagine how. Others might survive in even harsher environments through mechanisms we haven't discovered yet. The universe is vast, and it's filled with wonders. Some of them are violent supernova, black holes, gamma-ray bursts. But some are quietly beautiful, like a planet made of mirrors orbiting a distant star, catching the light and sending it back into the darkness. We found it because we looked. We understood it because we studied. And we share it with you because discovery is meaningless if it's not shared. If it doesn't inspire wonder in others, if it doesn't remind you that you live in a universe far stranger and more magnificent than everyday life suggests. You exist in the same universe as LTT 9779b. That planet is out there right now, reflecting light that began its journey before humans built cities. Before we invented writing, before we looked up and wondered what those lights in the sky were. And now, one of those lights, or rather one of those reflections, belongs to the brightest planet we've ever found. A world of metallic clouds and impossible survival. A cosmic mirror shining in the dark. If a planet can survive by becoming a mirror, what other impossible worlds are waiting to be discovered? Subscribe to explore them with me.